So it turns out I'm making this video directly after that tutorial video, which you may or may have not watched. And my coffee is just running out, which is not so great. So, you know, try and follow along. Turns out I'm really bad at drawing things too. I tried to draw stuff. I thought maybe it might make these a little more interesting, but I'm so bad that yeah, it's really not worth it. Fixed point methods. This is Math321 821. Fixed point methods are a generalization of the Newton's. Wow, no, they're a flexible. Fixed point methods are a flexible approach to root finding. They have other applications as well. So the idea is if f is a function from R to R, and well, I mean, it could be all sorts of things, but from R to R, and we want to find alpha, an element of R, so that f of alpha equals 0. Well, you've seen a bunch of methods. Also, though, we could find the fixed points of the function g of x is equal to x minus f of x. Okay, little proof of this. If g of alpha equals alpha, that implies that alpha minus x times alpha equals alpha. That implies alpha equals 0, so alpha is a root. Yay! If f of alpha equals alpha, 0, well, that implies that g of alpha, which equals alpha minus f of alpha, is equal to alpha, so alpha is a fixed point. Fixed points and roots, this says zeros, are related by clever choices of my function g. Other choices of g work quite well as well. F of x is equal to x minus some number times f of x is fine. G of x equal to x minus some function times f of x works perfectly well. As I think there's some condition on h here. I suppose we need h bounded, the absolute value of h bounded. Yes, bounded in some neighborhood about the root. Two. Another example is g of x equal to x minus some rather more arbitrary manipulation. Here, f is a number from the reals into the reals. So we have reals to reals to reals, f and capital F, little f and capital F. X goes to f of x, which goes to capital F of x. Great. Newton's method is an example of this. Remember, we need a bound. G of x is equal to x minus 1 over f dash of x. And as long as this is bounded, then this is a way to convert the root finding. Well, this is the algorithm of Newton's method already represented as a fixed point method. So the algorithm for fixed point methods is all the same. Oh, I can hear the washing machine. Let me go get that and come back. Won't be long. Seems a bit cliched really to say that when I'm just going to cut the video, doesn't it? Hello. Right. The algorithm for finding fixed points. For G, it's very easy. This is for arbitrary G. Start with some point. The next point is defined as G of x 0, and so on. So xi plus 1 equals G of xi. And if you think about that and plug it into here, you get xi plus 1 equals xi minus f of xi over f dash of xi, which is Newton's method. So Newton's method is already a fixed point method. You've seen it. We've done a proof of the convergence and error for Newton's method already, and basically with fixed point methods you're going to see it all over again. But fixed point methods are more general, and that's their point. They have a flexibility about them which makes them very good to work with. In class I mentioned Aitken's delta squared method. I'm not going to talk about it here. Look it up. It's a method that allows you to take a method for finding fixed points and speed it up. It's very interesting. I think it's very interesting. I think it's a really cool method. I'm going to jump instead directly into the first theorem. Let g of x be such that for all let g of x be such that there exists x0 inside whatever the domain of g is, which I'm going to be taking as r, but yeah. We need rho p greater than 0 and lambda greater than 0, lambda less than 1. I think it can actually even equal 0. Is that all? That's all. So that x0 minus g of x0, the error in the first iterate is less than or equal to 1 minus lambda times, that's meant to be a rho. Yes, that little rho p. And for all x dash, an element of x0 minus rho, x0 plus rho. This is the interval, closed interval, whose radius is rho about x0. I'm going to call this I below. So for all points in here, g of x minus g of x dash is less than or equal to lambda x minus x dash. Now it's worth noting that this is Lipschitz continuity, and that implies continuity. If you don't know this, please go look it up. This is worthwhile things to read about. Read about this if you don't know it. If you do know it, fine. You don't need to read about it. We'll go on page 3. Okay, proof. Oops, I haven't even included the conclusions. Then, the conclusions come in 3 bits. The first bit is for all I, xi equal to g xi minus 1. I know what my x0 is. For all I is inside my interval. 2. There exists alpha inside my interval, so that the xi converge to alpha, and xi minus alpha is less than lambda I rho. 3. Alpha is unique. The unique fixed point of g in the interval. These are pretty weak conditions. This is a fairly strong conclusion. This is a good theorem. This is a great statement of a good theorem. Not much is said here. You have to find these three numbers, x0, rho, and lambda, so that these conditions are satisfied. At that point, you get all sorts of nice things. Beyond Lipschitz continuity, I don't really mind what's going on with g at all. This gives g a great deal of flexibility, and it means that fixed point methods have been explored in a way which other techniques haven't. It's also one of the reasons why fixed point methods are so interesting. Alright, let's do the proof. So first I'm going to prove 1. Need to prove that for all I, xi is equal to g, xi minus 1 inside the interval. Okay. Page 4. This is inductive. So let's do the base case. x0 minus x1 is equal to x0 minus g of x0. And from the statement of the theorem, I know that x0 minus g of x0 is less than or equal to this, 1 minus lambda rho. And that's less than rho because lambda is less than 1 and is positive. So this implies that x1 is inside my interval. Base case done. Assume that for all I less than or equal to some v, xi is inside the interval. We're going to apply two tricks here, telescoping and this thing here, and the Lipschitz continuity. Three tricks. Amongst our tricks are such things as Lipschitz continuity, this thing here, and I always forget the joke. Monty Python, man. Gee, in my younger days, I used to be able to quote that by heart. Anyway, let's do this calculation. xv plus 1 minus xv is less than or equal to g xv. And by definition of the iterates, g xv minus 1, which is less than or equal to lambda times xv minus xv minus 1. Why is that true? That is true by Lipschitz continuity, and because I've assumed that everything's an I. Everything less than, for all iterates whose index is less than v, they're inside I. That's less than or equal to v, that's less than or equal to v. These are both in I. If they're both in I, then g is Lipschitz continuous, so I get to write that down. This is equal to lambda times the absolute value, g x v minus 1, the definition of the iterates again. You can see what's going to happen here. I'm going to do exactly the same argument as before, lambda squared. No. Well, repeat this a lot, and then you get down to, which is where we pop in this. Great. So now we have a bound for the distance between the points, which is good. Okay, so now we're going to use telescoping. xv plus 1 minus xv plus xv. I'm adding in 0. These things cancel to give 0. I can put that in. That's fine. Minus xv minus 1. And I'm going to repeat doing that until I get down to x1 minus x0. And now I'm going to chop it up into bits. This distance is going to be less than or equal to the distance between all these bits. Great, and I have a bound on all of these bits. It's there. So this is 1 minus lambda, lambda v rho, plus 1 minus lambda, lambda v minus 1. That's a v plus 1, that has a v. V plus 1 has a v. This is just a v, so if that was just v, that would be v minus 1, which is why I have a v minus 1 row. This is equal to 1 minus lambda v plus all the way down to 1 times rho, and you can work out what this is by multiplying through 1 minus. I always think of it as the proof of the geometric sequence, which it is, of course, in some variant, and hopefully that makes sense at some point. Anyway, lambda is less than 1, because I assumed lambda is less than 1. Lambda is less than 1. This is less than 1. This is less than rho, and that implies that xv plus 1 is inside I. The inductive proof is complete, and so 1 is true. Two. There exists alpha, an element of I, so that the xi converge to alpha, and xi minus alpha is the lambda I rho. Okay, right, so from above we know that prove that the sequence is Cauchy. That's what we're going to do first. So let's consider xm minus xm plus some p, not rho. I'm going to telescope this series, xm minus xm plus 1, because p is positive. I'm going to telescope upwards. xm plus 1 minus plus xm plus p minus 1 minus xm plus p less than or equal to, well, chop all of that up, xm minus xm plus 1, xm plus p minus 1 minus xm plus p, which is equal to, now I have a bound on this, sneak it in. We know that the step size of one iterate is bounded by this, so let's put that in. There it is. So v here, v plus 1 there, m here, so that is there's an m plus 1 there, 1 minus lambda m rho plus 1 minus lambda m plus p minus 1 rho. And again, if you multiply this through and do the algebra, this works out to be this. Okay, now I didn't write this down in class, and for that I apologize. I should have. The claim was that this implies that the sequence xi is Cauchy, and it does. Here I'm going to prove it. So, for all epsilon greater than 0, there exists an n epsilon, so that xm minus xm plus p is less than epsilon, which really means that we need lambda of n less than epsilon over p, and that implies this. Once you just think about it a little bit, again, because lambda is less than 1. So I is a closed interval. In particular, it's compact. So there's some facts in here that you should think about. Closed plus bounded implies compact in the reals. And the main point about compactness is, so compact implies that there exists alpha, an element of I, an accumulation point of the sequence xi. So that means that that means there exists a subsequence that converges to alpha. Why does compactness imply this? Well, in the reals you can take this as the definition of what compact means. If you don't know how this relates to compact, then I suggest you go and read about this. It is related to topology, and it's super cool, interesting stuff. At least I think so, which maybe that says more about me than it does about the mathematics, but anyway. Okay, so I've proven that there exists some alpha that some subsequence converges to, so now I need to show that there is a sequence, but my sequence is Cauchy, and that implies that the full sequence must converge to alpha. Woohoo! Surprise! Okay, great. So now I've got this bit and that bit. I need to show this bit. This is not super complicated. It's very similar to everything else, and hopefully it's kind of clear what's going on. Start with the condition I need to prove. Xi minus alpha. Well, this is equal to G Xi minus 1 minus G of alpha. Oh, I can't claim that quite yet, can I? Because I haven't shown that alpha is a fixed point. Why is alpha a fixed point? G is continuous. So I've got to stop saying haven't I? G is continuous, so sorry about that. Should stop it. Anyway, we know that I did it again. Friggin' Xi converges to alpha. G is continuous. This implies that G Xi converges to G alpha. But the sequence Xi is equal to the sequence Gxi and is Cauchy. So G of Xi converges to alpha. And that implies, by Cauchy, that G alpha equals alpha. It also happens to imply uniqueness, but we'll get there in a moment. Because the limit points of a Cauchy sequence are unique. Cauchy sequences are great. Anyway, Xi minus alpha is equal to G Xi minus 1 minus G alpha. By construction, both Xi minus 1 and alpha inside lambda, so inside my interval I, so I can write this down, and then I can iterate the whole process. Which gives us the claimed result. Beautiful. Page 5. Probably page 6. Page 7. This is uniqueness. We know that alpha is a fixed point, so we only need to prove uniqueness at this point. It actually follows from Cauchyness, but we'll prove it here. Prove it by contradiction. Suppose exists beta in I, so that G of beta equals beta, and alpha is not equal to beta. Then 0 is not equal to alpha minus beta. equals both fixed points divide by alpha minus 1, which is not equal to 0. That's fine. Lambda is bigger than 1. This is a contradiction. It implies no such beta exists. So alpha is unique. Woo! Finishes the proof off. Nice general proof. If you've been paying attention as you go, go have a look back at what this proof looks like in comparison to the proof of convergence for Newton's method. And you should find that, suspiciously, they're the same thing, or very, very similar. And that's because Newton's method is already a fixed point method, and fixed point methods have a flexibility to them that allows you to prove theorems like that have weak conditions and nice, strong conclusions. And that is the best type of theorem. For those of you who care about general relativity, the singularity theorems have often been criticized for having strong assumptions and weak conclusion. A bad type of theorem. Lemma. Not a particularly exciting lemma. Function continuously differentiable inside our interval that we're thinking about. Not going to define everything again. Is if is such that so if it has bounded derivative on our interval less than 1, then f is Lipschitz with Lipschitz coefficient lambda, i.e. Let me say x dash and x for all x and x dash inside our interval. Most often the g's that you work with will be differentiable, continuously differentiable, so this result is great. Bound the derivative, show that something's less than 1. Bingo. If the derivative is not less than 1 but it is bounded, then divide it by a constant and make the derivative of the new function less than 1. Proof is pretty easy. Mean value theorem implies there exists zeta inside inside the interval x and x dash, so that I'm just being super pedantic and a bit careful here. X fx minus fx dash is equal to f dash epsilon x minus x dash, which implies that so as this interval is a subset of I, we know that the absolute value of this is less than the absolute value of that, which is less than the absolute value of this, times the absolute value of that, which is less than or equal to, well, we have a bound on that, so that's a lambda. Hey presto, we're done. Boom. Proof completed. Phew. And that is that. Next up, errors. So you can this talks about error, of course, because we've got convergence and error terms, but that's the error in our approximation, not the numerical error. Turns out with fixed point methods you can even discuss the numerical error in a nice general way. But that's for another time.